Okay, so in the previous video, I explained that we can predict the outcome, and then still there are remainders, not explained part. We define that as the residual. So the residual epsilon hat, it is, you can interpret this as an estimated part of the error term, is the difference between the observed outcome minus the predicted outcome. Okay, so you can understand the residual as a transformed random variable, and you have 12 observations of the residuals. Okay, and then now we are going to decompose the observed outcome into this. So this is the observed outcome, and we predicted the outcome to be this much. That is what we could explain by the regression model, right? Plus, if there is a difference, that is the residual. That is the unexplained part of the observed outcome, right? So the observed outcome is decomposed into explained part plus the unexplained part, okay? Then obviously, we would like to maximize the explained part, the portion of the explained part, and minimize the portion of the unexplained part. That is what we want, our goal. So if the unexplained part is small, then on the scatter plot, the observations will be closer to the trend line, fitted line, and also your prediction of y will be more accurate, and in the correlation coefficient, the relationship between x and y is stronger, right? So graphically, this is a better prediction than this one. The bottom graph shows the perfect prediction case, but of course this is unrealistic. But when you compare the top graphs, we would like to have something like the left one. So the observations are closer to the line, or the deviations are smaller, right? The residuals are smaller overall. That is our goal. We would like to make a trend line look like this. Okay, then based on this idea, we can do two different things. First, I will explain how Excel calculates those numbers, right? The OLS estimators are calculated, but how are they calculated? Now I'm going to explain that. And second, we can evaluate how much your model can explain the outcome, right? That is an evaluation process. Okay, so let me first explain how those estimators were calculated. Okay, so it goes back to the original question. So we have observations, and we need to estimate beta 0 and beta 1. What is the best estimator? Right? So to answer that, my answer is we are minimizing the residuals. That is the simple answer, right? How do we minimize that residuals? So think about this. The residual is defined this way. If you estimate beta 0 and beta 1 this way, your residuals will be defined this way. Our idea is we are going to square, because the residual could be positive and could be negative, but when I say minimize, that means we would like to make the residuals as close to 0 as possible. We'd like to make it as close to 0 as possible, right? So then we are going to minimize actually the distance from 0, distance of the residuals from 0. Then the distance, remember, we are going to use the square as the distance because it could be negative or positive. By taking square of the residuals, everything is positive, and it will, this is a distance because as the residual moves away from 0, the squared residual will increase. So we will interpret the residual square as the distance from 0, and we will minimize the squares. But as I said earlier, there are as many residuals as the number of observations. So we are going to sum all the residuals distances, and we will minimize the total distance. Okay? So if there are 12 observations, you can calculate the residuals distance for 12 different observations. And then what we are going to do is we would like to minimize the sum of those distances. That is called residual sum of squares. Residual sum of squares. And on Excel, so on this table, now we are going back to the ANOVA table. ANOVA table, like earlier we learned what this means. Now we are done with the third table. Now we go back to the second table. So here, SS stands for, it's short for the sum of squares, right? Sum of squares, and there is the second one. Second sum of squares is the residual sum of squares is this. So this number captures the sum of all the squared residuals. That is how much you cannot explain. You want this to be smaller, right? So back to here. So this is sum of squares. Residual sum of squares, okay? And then our estimator is the ordinary least squares. So this estimator chooses the estimators that minimizes the sum of squared residuals. So sum of squared residual. So this is the actual outcome, observed outcome minus predicted outcome. So inside the square is the residual. Okay? So it's mathematical problem. You choose beta 0 and beta 1 that minimizes the distance. So it is literally like a similar problem like the maximization of utility, right? So you can calculate the first order conditions and the second order conditions, and then you find the solution. The solutions are the ordinary least squares estimator. Okay, so least squares is a more general class of estimators. Later, as I said, when you have variations of regression models, you change the setup of the regressions. But here, we do not just consider any variations, but just simple sum of squares is what we are going to minimize. So they are the ordinary least squares estimator. That's what Excel calculates. So those numbers are based on the minimization problem. So Excel minimizes the residuals. Okay, and residual is that's the key idea. Okay, so back to the simpler example. So this is the simpler example about cost and output. We learned what these mean, and now we learned what this means, right? SS stands for sum of squares, and we are minimizing residual sum of squares. So these values, these coefficient estimates, minimize this value. You cannot find any other coefficients that makes the residual sum of squares smaller than this. That's the story, right? When you choose beta 0 and beta 1, these values, then this sum of squares will be the smallest possible value. For example, let me show you the other cases. For example, if you try other values of beta 0 and beta 1, then the residual sum of squares will be greater. Like I show you two different cases. So blue, like green. The blues are the observations, and green is when you choose beta 0 to be 8.1, beta 1 to be 2.4. If you apply these numbers, then if you try these numbers, you can calculate the new residuals, right? And the summation will be 29.48. which is greater than the optimal, the minimum residual sum of squares. And when you try even more different numbers, like beta 0 is 5 and beta 1 is 3, if you try these numbers, then some of the residual sum of squares become even larger, like 56. So that is red. And as you see, um, like on the graph, the difference is not that big. But when you calculate the residuals, then you see which is really better, right? So it's hard to see what happens on the graph. So we mathematically solve out the best trend line. Okay, that's what's behind the ordinary squares. And mathematically, the minimization problem, you may think the minimization could be more difficult, but actually it's pretty simple calculation. In the end, if you solve out the minimization problem, the slope is just ratio between covariance and variance. Covariance between x and y divided by the variance of x. Or it's also related to correlation coefficient. And the intercept depends on once you calculate the slope, after calculating the slope, you calculate the intercept using the means, averages, okay? So I will skip this question. So you know how to calculate covariance, you know how to calculate variance, you know how to calculate the sample averages. So like calculating those things are pretty simple on Excel. So actually the minimization problem is not that hard for the computer to do, right? Computers can do that pretty easily. So then you can just calculate those coefficient estimators by calculating sample mean, variance, and covariance, and then you know how to calculate them, and you can calculate the beta from those numbers, which is also pretty straightforward. So also, this formula is not that important to you because this is computer's job. You don't need to memorize those formulas, but I just wanted to show you that in the end, the regression estimators are nothing super special. It's just some related to what you learned, and very basic measures are related to those ideas. Okay. And I also skipped this question. So if you calculate the sample mean, sample variance, and covariance, then you can calculate the beta, right? So then you can calculate beta first, the slope first, and then always the slope is calculated the first, and then the remainder is calculated, the mean is used. You use the sample mean to calculate the intercept. Intercept follows from the slope. Okay, so I will skip those calculations. It's not that difficult. So the differences are rounding errors. I will skip those things. The next topic is, okay, we calculated the residual sum of squares. We square the residuals and sum them over observations. Okay, and sometimes it is referred to as sum of squared errors, depending on the textbooks and the fields of study. Different names are used, but let me follow Excel. Okay. So, and remember, the residual sum of squares measures how much you fail to predict, right? That is the amount of unexplained portion of outcome. And then, using the similar idea, we can measure the amount of explained part. How much you could explain, it can be written in this way, right? So this is measure of unexplained, but this is measure of explained portion, right? So y hat is your predicted outcome. So you predict outcome by y hat, and you you subtract its mean and take square and sum, right? Remember, this, if you divide it by n-1, actually this is a variance formula, right? So it is kind of variation. You can explain this as a variation, And then this particularly measures so if you divide it by n-1, then that is exactly the variance of your predicted outcomes, right? Predicted outcomes. So I am going to explain this as the sum of squared deviations in your prediction. That is the variation explained by the regressions because the predicted values are generated from the regression model. So you could explain this much variation, right? This is explained variation. And finally, one more thing. So this is regression sum of squares, which is this one, right? Sum of squares, let me write the full name. Sum of squares. We learned residual sum of squares earlier. So 29 is how much you fail to explain. Then on the other hand, 395 is how much the regression model could explain. The regression explained 395, right? So idea is same. We measure the distance, either you unexplained or explained. And the third is total sum of squares. This is the variation in the original outcome, right? So of course, remember, the original outcome was decomposed into explained and unexplained. So this is the total variation in your original observations that is also given in here, right? Total sum of squares was 425. But out of this much variation, you failed to explain 29. But you could explain 395. And so we calculated 3 variations. And what's interesting here is the total variation is the sum of explained variation plus the unexplained variation. So your data has certain variation. Then your regression model could explain a certain portion of that, and the other portion is not explained. So it's a perfect, clear decomposition of the variation in your data. Then we can use this decomposition, how much we explain and how much we couldn't, and you use this to measure how well your model explains the outcome. So I told you these are the sum of squares we just learned, and then we define the coefficient of determination. How much your regression determines the output. Your regression model determines explains some part of the output, and how much is that? That is called the coefficient of determination. So out of total sum of squares, the regression model explains regression sum of squares, SS, and that is how much you explain. In here, back to Excel, so out of 425 variation, your regression model could explain 395. So that is, you can calculate the ratio, right? If you divide it by this, it is 93%. About 93% of the variation is explained by the regression, and that is this number, right? R square, R square is the ratio of explained part out of the total variation, right? So you could explain the regression model in our simple example. The simple example could explain about 93%. And then of course this is a percentage because it's always in between 0 and 1, right? If R square is 0, that means the regression does not explain anything. But if R square is 1, that means your model explains 100%. That means perfect prediction. Both are unrealistic, right? So, and also you may interpret this as the strength of the relationship between x and y. Okay, so R square is another common measure we use to evaluate how good your regression model explains the outcome. Okay. So in our example, 93.707% of the variation was explained. And what is interesting here is the reason why we call this R square is because this measure is the square of the correlation between actual outcome and the predicted outcome. So you want the predicted outcome is as similar with the actual outcome as possible. So if the correlation is close to 1, then your prediction is good, better, right? The higher the correlation is, the better your prediction is. So, but the sum of squares is like in the sum of square measures, everything is squared. So that's the intuition why we take square of the correlation, right? So it's also related to the correlation coefficient of the actual outcome versus the predicted outcome. Okay, and if it's 0, there is no linear relationship, there is no relationship. If it's 1, the perfect prediction, which is also unrealistic. Okay, so in this video, I extended the residual analysis to calculate regression sum of squares and total sum of squares. And also I showed they are perfectly decomposed, so we can obtain an interesting measure of accuracy of your prediction, which is R squared. Okay, so R squared, like here, I will explain other variables. R squared, this is coefficient of determination, but so usually we just call this R squared rather than coefficient of determination. R squared is the common name, and multiple R, this is correlation between actual and predicted outcomes, right? So the multiple R is nothing special but correlation, and its square is R square. So this is same as R square. If you take square of the multiple R, then you get R square. So that's why we call this R square. And adjusted R square is not relevant here. So adjusted R square is when you have, it's relevant when you have multiple x variables. So when you have more than one x variables, then the R square formula need be adjusted to reflect the number of number of variables you use. So for now, it's not that relevant, right? Later, I will explain this later. And a few more discussion about here. So DF means degrees of freedom, right? So, like when you calculate the residual, before calculating residual, you have to estimate 2 parameters. So out of 12 observations, you consumed 2 information to estimate 2 parameters. So your degrees of freedom is only 10 because you consumed 2 information out of 12. And when you calculate total variation, you consume only 1 information when you calculate the sample average. So the first stage, you estimate the sample average and then calculate the deviation and square and sum. So when you calculate the sample average, you consume 1. So in that sense, you have 11 degrees of freedom. So degrees of freedom is the amount of information you can utilize to calculate the measure. So that's the intuition. And regression sum of squares is 1 because it's decomposed. So when you calculate the residual, you consumed 10. So the regression has only 1 remainder. MS is mean squared errors. I will just skip that. So mean squared error is mean squared means, so it is average. So you divide the sum of squares by the degrees of freedom. Like this divide by this. So it's like I said, if you divide the sum of squares by the sample size, that is a variance. So it's kind of variance of the residual. Okay. And so what's interesting is this is related to the standard error, because if you take square root of mean squared residuals, then you get the standard error, right? So like mean squared residual is the variance of the residual. If you take square root of that, that becomes standard deviation, right? And this is F statistic. It is another hypothesis testing, which I'm not going to explain right now. And significance is literally the significance, the p-value of this hypothesis testing, right? So I'll skip these two for now. Okay, so I explained the idea of coefficient of determination, and that's how we evaluate your model explanation power. Okay, so in the next video, I am going to move to the real data again, to the education example, and we'll finish the lecture in the next video. So thank you for watching, and look forward to the last video of this semester. See you later.